Okay then. Okay, one more time. Am I audible clearly?
Yes, sir.
Okay, thank you. Thank you so much. So okay, then welcome back uh, to this problem solving session for the introduction to fluid mechanics course, and so this will be the final problem solving session. And again, as a gentle reminder that we have gone through rigorously gone through the basics of the fluid mechanics, started from knowing the continuum hypothesis, then about the fluid properties, this viscosity, density, then intensive and extensive properties. Then again we looked into static pressure, then dynamic pressure, then stagnation pressure, and again we looked into various flow measuring devices such as venturimeter, orifice meter, pitot tube, orifice, and again we started with about learning about the hydrostatic forces on body submerged bodies. Then we looked into then we basically looked into the dynamics of fluid mechanics, like basically the mathematical formulations, RTT, mass conservation, momentum conservation, and then looked into how we derive the Navier-Stokes equation from the linear momentum conservation, and what are the assumptions that we basically looked into for deriving the Navier-Stokes equation from the Cauchy's momentum equation. So this was a general framework that we looked upon up to till last class. Also, we looked into a bit into the uh, special cases or special geometries for which the Navier-Stokes equation could be solved exactly, mainly because the non-linearity is inherently removed, and then it makes the equation linear. Plus, most of the terms are cancelled out, so that the equation becomes a simple differential equation, ordinary differential equation that can be easily solved. And also the boundary conditions are clearly defined, so that does not make any much of a difficulty for us to solve. It becomes a simple differential equation. So we look into that. So I also asked both of you, since I guess Priyanka was not didn't look through the co-ed flow. So I hope you looked into the co-ed flow, and the remaining lectures where Professor Chakraborty mentioned about some exact solutions of Navier-Stokes equations, such as flow between two parallel plates, basically plane Poiseuille flow, then simple co-ed flow, then the problem that we looked into previous session, that is the shear pressure driven co-ed flow, then flow between two rotating cylinders. I guess this was also discussed by Professor Chakraborty. So one of such problems that we will look into today is the Hagen-Poiseuille flow, or pipe flow, or basically a fully developed flow through a circular pipe or a tube. So this is the topic for today's discussion. I will just go through the derivation. I have derived the entire derivation from the start. So I will briefly go through the steps. I won't emphasize much on each and every point. So at whatever the point, like you feel that I need to repeat, or you find that it is difficult to understand, you can just stop me right there and then ask. So that's all will be our agenda for today. And then we will briefly go through the concepts of flow through pipes or ducts, which is the last topic for this course. And then finally we will look into the dimensional analysis, the brief concepts of dimensional analysis, and that will be all for today and this course as a whole. So I guess it's fine. So let's start. So for a similar to plane Poiseuille flow, in this case pipe flow or Hagen-Poiseuille flow, fully developed pipe flow or Hagen-Poiseuille flow is also an internal flow. That is, the flow is the entire duct or geometry is filled by the fluid, and it's how the flow is generated. And basically these pipe flows are pressure driven flows. uh, I guess boundary layer flows that I briefly discussed in one of the sessions is out of the scope for this course, or like has not been included in this course, but it's also one of the very crucial topics, crucial fundamental topics in the domain of fluid mechanics or fluid dynamics. So I encourage both of you to look into it whenever you get a chance, because without the concept or the clarity of the concept of boundary layer theory, I think the understanding of fluid mechanics is incomplete. So I encourage both of you to look into the concept of boundary layer flow. I'm basically saying that because the boundary layer flows are basically, or flow, or one of the most popular cases or by which we understand or try to understand boundary layer flows is through flow over flat plate. Flow over a flat plate. So these types of flows are inertia driven. It basically means the inertial energy of the flow itself, the incoming flow that comes with, say, u infinity. It is the energy of the incoming flow that drives the flow over the flat plate, overcoming the viscous stress, viscous forces. Okay, but in this case, the flow is driven. It is not that the viscous forces are not there. The viscous forces are what that are needed to be overcome for the flow to occur, and these viscous forces are overcome by the pressure difference generated between the ends of the pipe. Okay, so again in this diagram, I guess I would not like extensively discuss about the diagram. I guess it was extensively discussed in the session, both in the while discussing the Hagen-Poiseuille flow and the flow through pipes. So I don't think I would like to repeat for both the cases, but still this region, where the flow is developing, or basically the velocity profile is developing, is known as a developing region, or the entry length, or developing region, and the length up to which this developing region occurs is known as the entrance length. So basically it is a region where the boundary layers from both of the edges, both of the ends of the, I won't say both of the ends, it's a circular pipe. So it is the region where the boundary layer from the surface of the pipe develops and converges into the center line. And as I remember, as Professor Chakraborty discussed, that why do they converge in a center line? It's mainly because of the geometry, the symmetry of the geometry and the symmetry of the boundary conditions. It is because of this that the flow converges in the center line of the pipe itself. So in the developing region, the velocity profile is a function of both x and y. Okay, it basically means that say if this is our, okay, I won't say x and y since we are using cylindrical coordinates, so let's be consistent with our coordinate system. So let's say I use r and z. That would be much better. So basically means that while the flow flows through this developing region, the velocity profile changes from different z locations. Basically means that the velocity profile here would be slightly different than the velocity profile that is say some distance away from the initial z coordinate. And finally, at the point where the up to the point where the I will say beyond the point where the boundary layer converges, beyond that point, the flow is called fully developed, and the velocity profile basically becomes only a function of r, or the r coordinate. So basically it means that for a fully developed region, u is only a function of r, and this fact that u is only a function of r can also be obtained from the mass conservation. So I won't go through detail of this derivation. So let's see. Okay, from continuity or mass conservation, we can say del rho by del t is equal to nebula of divergence of rho v, rho and the velocity vector. Okay, so I write so it is then written in the cylindrical coordinate systems, because our geometry is in the best way it could only be solved by, or it can be solved appropriately by the use of cylindrical coordinate system. So we use cylindrical coordinate system, and then again we use an assumption that the flow is fully developed. So the velocity profile is not a function of z coordinate. So d by dz is 0, and again we assume one of the assumption is that the flow is axisymmetric. So any derivative with respect to the theta coordinate, with respect to theta direction, is 0. So it means that the flow is axisymmetric. And again the conclusion that comes from the there's a conclusion that comes from the continuity equation is that okay, so the conclusion that comes from continuity equation is that the radial velocity component, it is Vr, is not a function of r. And again the boundary conditions are also like that at both of its ends, that is basically, say if our coordinate system is located at the center line, so at r equal to r, Vr is 0. That basically happens because of no penetration boundary condition. So we get that Vr is not a function of r, and we find that Vr is equal to 0 for all r because of this boundary condition, because it is not varying with r. And since it is 0 at the 0 at the boundary at r equals 0, similar to the plane positive flow case, you find that because of this, in the plane positive flow you found that the velocity component along the y direction was 0. Similar to that, you find that the velocity component along the r direction is also 0. Okay, and again for this problem, the axisymmetricity of the flow does not confirm that the flow the v theta component is 0. But for our simplification, we take one more assumption that there is no swirl velocity, or the swirl component of velocity is 0. So basically the v theta component, we also take it to be 0. So keeping all these assumptions and the conclusion from the continuity equation, we apply those assumptions and conclusions from the mass conservation and the boundary conditions to the momentum equation along the r, theta and z direction. So this is the theta component of momentum equation. So cancelling out all the terms, we get that we get all the terms equal to 0. So basically it becomes that the body force term along the theta direction is identically equal to 0. So this is the conclusion from theta momentum equation. Again from the r momentum equation, we get that dou p minus dou p by dou r plus rho br is equal to 0, and br equal to minus g cos theta is I guess this is out of is by decomposing the body force component along the r and z direction. So I won't go to the derivation again. So our conclusion we get is that dou p by dou r is equal to minus rho g cos theta. Okay. So again we look into the z momentum equation. So from the z momentum equation, we our governing equation takes the form dou p by dou z is equal to mu 1 by r dou by dou r operated over r dou v z by dou r minus rho g sin theta. Again this is by decomposing the vector along the r and the z direction. So body force vector along the r and z direction. So this came out of that. So we take one more simplifying assumption, that is, from the r momentum equation we got that, as we saw, dou p by dou r minus dou p by dou r minus rho g cos theta is equal to 0. So we take one assumption that the radius of pipe is much more smaller than the length of the pipe, and it is basically the scenario for most of the cases. Like wherever we find pipes, and basically it is to say for supplying water to our homes or industries, we basically see that the length of the pipes is much larger than the radius of the pipe itself. So taking assumption that so it will basically mean that say if I draw the pipe like this, say if it is much more smaller, so and sorry, so if it was g, so we get it as minus g cos theta and minus g sin theta. Why minus? Because of the direction of the force compared to the initial choice of our coordinates, that is r and z. So okay, so we can clearly see that if the radius of the pipe is much more smaller compared to the length of the pipe, this component basically becomes insignificant compared to the minus g sin theta component, basically along the z direction. So this component becomes much more smaller compared to compared to the axial component. So that's why, neglecting this, we can say that dou p by dou r is equivalent to 0. So it's basically in the order of magnitude compared to rho g sin theta, this is almost equivalent to 0. That's why we can efficiently take that dou p by dou r is equal to 0. So this basically gives us that p is not a function of r. So finally we can write that p is only a function of z, because d by d theta of all the terms were 0, as our initial assumption that the flow is axisymmetric. So the only direction along which the derivative for p can exist is along the z direction. So p is only a function of z. So our final governing equation that remains is the z momentum equation. This is basically dou p by dou z plus rho g sin theta plus mu 1 by r d by dr. Now this is the complete derivative, because again vz is only a function of r, as a conclusion from the conservation equation, or as a conclusion from the mass conservation, and also as a conclusion from the assumption that the flow is fully developed. So v becomes only a function of r. So it becomes a complete derivative instead of a partial derivative. Again, then to simplify this term a bit, we take instead of this whole term, we take a pressure head as P star is equal to P plus rho gz sin theta. Rho gz sin theta. So this can be basically consider as a piezometric head. This is basically considering the elevation along static elevation along with the existing pressure difference. So we consider piezometric head P star to simplify this calculation, that instead of considering this term explicitly, we include it in the P term as a piezometric head. So we finally get dp star by dz is equal to mu 1 by r d by dr r dvz by dr. So again I will not go through each of the steps. So I guess the steps are clearly visible on the screen. So if any of the steps that you see are unclear, so you can stop me. So the final velocity profile that we get is this, actually, that v of z is minus c r square for mu 1 minus r square by r square, where c that we have taken is equal to c is an constant that we uh, c can be c is equal to dou p star by dou z. Yes, so c is equal to minus c equal to dou p star by dou z. Yes. Again, this statement that dou p star by dp dp star by dz has to be negative to drive the flow in the positive z direction. So this, I guess, you clearly know why, because of the requirement of favorable pressure gradient. So I don't think I need to repeat this again. So again, yes, so here v bar, we denote v bar, v bar denotes the average velocity through the pipe. Okay, so just as okay, since you have not read about scaling, but let me say briefly about scaling is that see, in the case of flow through a flat plate, flow over a flat plate, the x component of the velocity, okay, say if it is x and y, and initially our flow is along the x direction, which is say u infinity. So the velocity component along the x direction, that when we non-dimensionalize our velocity components, basically to simplify our equations or non-dimensionalize our equations, so each and every parameter, that is velocity and pressure, has to be non-dimensionalized to get a non-dimensional equation. Okay, also the derivatives as well, and to do that we have to use some scaling terms, basically how these velocity components will scale, like with respect to which with respect to whom our velocity would scale. Okay, so a non-dimensional term could vary from 0 to 1. So it basically means that our velocity scaling basically means that our velocity component that we are choosing may vary from maybe 0 and may reach up to u infinity. Okay, and this is our scaling. And actually I can say that this is not a correct way to say that, but scaling is in the sense that the order of magnitude of our velocity would scale as u infinity. Basically means that order of magnitude of our velocity component would scale as u infinity. Okay, is this clear, or I have to explain it a bit more? Order of magnitude of u scales at u infinity.
So could you please repeat just once?
Okay, sure. See, or I guess I have to tell you about order of magnitude a bit. See, say say that our u infinity is 5 meter per second, say, and our velocity profile at this region, say it is this. Say I want to measure the velocity at this point, okay, and I found out to be around 3 meter per second. Okay, I insert you through the means of some calculation, mathematical calculation, or even through some experimental means. If I was able to measure the velocity at that particular point within the boundary layer, say, I found it out to be 3 meter per second. Okay, so if we so 3 meter per second, in a much simpler sense, I can say that 3 meter per second is almost similar to 5 meter per second, right? But if we like compare this with say then okay, then it's very much similar to 5 meter per second. So basically means that 3 meter per the order of magnitude of the velocity at this point scales similar to the u infinity. It is almost similar, the order of magnitude remains the same. But say like if we were to compare this velocity say to 100 meter per second, say the motion of with the speed of modern day racing cars, maybe I am maybe I don't know a proper example, but say it is 100 meter per second. So I cannot say that 3 meter per second scales as 100 meter per second. It's just the magnitude I'm saying. I'm just trying to try to make you understand the difference in magnitude. How the difference in magnitude is quite extensive in this case and quite not so much different in this case. Could you understand the difference? Like how 3 meter per second is quite different than 100 meter per second physically also and by magnitude wise also, and 3 meter per second is quite similar to 5 meter per second both physically and magnitude wise. Is it clear?
Yes, sir.
Yes. So say if I have given you three velocities. Say v1 is 5 meter per second, v2 is say 10 meter per second, and v3 is 500 meter per second. So if I asked you like how do you say v1 is scales as, like scales as, so you can, so what would be your answer?
It is similar to V2.
Yes, similar means basically you can say that it scales as v2, like if you're basically it has the similar order of magnitude as v2. So actually the essence of these order of magnitudes becomes much clearer while dealing with boundary layer theory. How the order of magnitude, the change of order of magnitude can simplify or modify our governing equations, and it is because of this change in governing equations the boundary layer theory is so much successful, because we get a different scale along different direction. Like eventually if you read you will find that along the x direction our scales our x coordinate scales as the length of the plate, and the y coordinate scales as the boundary layer thickness. Okay, why? Because a considerable change in the flow physics along the y direction takes only at a length scale of delta, that is basically the boundary layer thickness, and a considerable change along the x direction takes along the scales as the length of the pipe and not as delta. Like if you were to scale x as delta, you will basically find no considerable change or measurable change to even conceptualize the boundary layer theory. Like you won't find any change, you will find it much similar. The flow physics say if it is equal to delta, say the flow physics at this region is quite similar to this region. So there is no point of scaling our flow parameters where there is no considerable change, right? So that's why we scale it as L. Okay, so I think I extensively discussed about order of magnitude. So I will basically say that why I wanted to say is that for flow in a flow through for a flow through pipe or flow through flow between two parallel planes, the order of magnitude of the velocity scales as the average velocity rather than the free stream velocity that you treat. And basically since all of these flows we assume it to fully develop, the shear or the concept of free stream velocity does not come into picture. So basically we say that the flow is fully developed, so it is the average velocity by which it is by the order of the average velocity by which our velocity in the flow field would scale as. And that's why it is very important basically to understand the concept of average velocity. So I guess this also I discussed in one of the problem solving sessions, how to derive the average velocity. Basically say if you can say that say I will just briefly again discuss it so to make it clear. So it basically means is that if this is our pipe and say this is our original velocity profile, okay, so now what we want is that we don't want to do the integration, like we are quite do not want to go through a tedious calculation of the velocity profile, then do the integration and then find out then do the integration to the elementary area, that is 2 pi r dr for a cylindrical coordinate system, that basically the ring shaped elemental area. We don't want to deal with that. Say we know the area of the pipe, that is pi r square. So what we do is we basically assume a uniform velocity profile such as this one, the blue one. Okay, I guess it is clear. So basically assume a uniform velocity profile and say that if it were the velocity uniform velocity profile through this region which has a magnitude of say, then multiplied by pi r square would basically give us the flow rate through this region. But that is actually not the case. Why this uniform velocity profile is not valid? Why it is not valid?
Because of the boundary layer.
Yes, because of boundary layer, basically because of viscous effects, and most importantly, to be more clear, because of the no slip boundary condition. So the velocity at the boundary walls should be 0. So this would actually be the black one should be our velocity profile. But say if it were the case that we are assuming uniform velocity profile, and so would be that uniform velocity profile or velocity that if it were to exist in this confinement, so this velocity profile multiplied with the area of this spike would give us the mass flow rate. So it will basically it will be equal to basically equal to u of z, because u is a function of z. U of z, I'm sorry, it's not u of z actually, it's u of r. U of r 2 pi r dr. Okay, so it's basically the case, and by equating this, basically you find out the expression for mean velocity, okay, or the average velocity. So this is the concept of average velocity. So in this expression, basically what you need to do is you substitute the value of the velocity value of Vz, that is basically the velocity profile that you obtained here. So once you substitute the velocity profile here, you will find out that Vz by V can be written by this expression. So it basically tells us that we will get a parabolic velocity profile with respect to r, since it varies as r square. That's why we get a parabolic velocity profile. Again, then we look into the expression for wall shear stress. Basically, why this expression is valid? Because of the case that the fluid being Newtonian. So this fluid is Newtonian. So again, we use this expression. Sign convention, I guess, basically because of the choice of our coordinate system. So it is mentioned there. Negative sign is because the r direction points inwards towards the wall from the center line. So we want to measure, like, our coordinate system should be here, but we are measuring r to be along this direction. Since they are in opposite direction, we have a minus sign to compensate that. And more importantly, this minus sign does not makes much of a difference. Okay, you are basically interested in the magnitude. So say if you say positive sign means refers to the shear stress provided by the fluid on the wall, you can basically say the minus sign will basically give us the shear stress that would act on the fluid because of the presence of the wall. So it does not cause much of a difference. So what we are basically interested is in the expression itself, so and its derivation. So that's what more important. Okay, so basically this is the expression. I guess we discussed it extensively on the previous class while discussing on the constitutive relationship. So VR is 0 because we found out from the mass conservation that VR is 0 throughout the flow field. So VR is 0. So we are left with mu dou Vz by dou r. So once we have the expression for Vz, we substitute the expression for Vz in this expression. So we finally get that tau wall at r equal to r. While at wall, then radius will be equal to r, right? So tau wall at r equal to r would be given by 4 mu V average by r. So the coefficient of friction is again obtained by dividing the shear stress by the by half rho v square. So we get by substituting this, we get that Cf, this coefficient of friction, basically varies as 16 by RED, where RED is the Reynolds number. RED is the Reynolds number based on the diameter of the pipe. Okay, rho V average D by mu. Okay, again out of curiosity, okay, say that we are, instead of dealing with an internal flow now, we are dealing with a flow over a flat plate, okay, a boundary layer flow. There also Reynolds number exists, right? Say RE
Yes, sir.
yes. So how do we evaluate the Reynolds number in that case?
We take length of the plate.
So the D here in this case would be replaced by length of the plate, right? And more accurately, if you can say, at every location the Reynolds number would vary. So it will basically mean it will be rho V average X by mu, right? And I guess I discussed this, maybe I discussed it, I may not have, so I just forgotten that, but still, see, a Reynolds number should basically be rho V bar LC by mu, where LC is the characteristic length scale of the flow field. Okay, so can any one of you please tell me like what a characteristic length scale means?
So we take it as the ratio of diameter to perimeter.
No, actually, diameter to perimeter will give us a, I guess, a non-dimensional number, right? But it is a length scale. It will have a unit. Diameter is also a scale of, it has a scale of length, and perimeter also has a scale of length. So even if you have to divide it, say if the definition was correct, so it would give a non-dimensional scale. So that's not correct, right? So that's not the case. Characteristic length scale. So okay, it's fine if you do not know, because like it's a, I won't say much advanced, but it's a advanced thing or difficult thing to understand, but it's an advanced concept, I could say. So a characteristic length scale basically means the length scale along which a considerable change in the velocity takes place, or you can say flow property, but since it is the velocity or it makes the pressure that we consider, so we can say that it is a length scale along which a considerable change in the velocity takes place. So in the case of flow within a pipe, or flow within a pipe, the characteristic length scale along which a considerable change in the velocity takes place could be R or diameter as well. So it depends on whichever one you choose, but most of the cases diameter is the one that is being chosen, so it is a more popular choice. So basically for these cases we define the Reynolds number as rho V D by mu. For flow or flat plate, the velocity profile changes from every x location, so that's why the characteristic location would be the x coordinate itself. That's why we define the Reynolds number as rho V x by mu. Again, for a flow between two parallel plates, the characteristic length scale would be flow between two parallel plates. The characteristic length scale would be
Height between the two plates.
yes, absolutely correct. So if we represent it by h, then h or L, then that would be the characteristic length scale. Okay, but again, say flow between two parallel plates, like I can say it's a hypothetical case, right? It's a hypothetical assumption where we assume that the length scale along the perpendicular direction, basically if we were to see the plate like this, if we had the plates arranged in this manner, say these were the two plates, so we basically assume that length along this direction is infinite, right? We assume the plate to be infinitely large along the z direction, right? So a more physically possible or physically accurate case would be flow between a rectangular duct, right? Flow between a rectangular duct is a more physically possible case. So in these cases, again, the characteristic length scale can be chosen in a different manner, or actually, as I guess as I remember from lectures, this length scale is chosen to to compare these flows to flow between flow within a pipe. Okay, since so that we can substitute say d is the characteristic length scale for flow between flow through pipes, and we assume that we can consider these two flows to be similar because of the case that both are in both the cases flow is the fluid is completely filling our confinement and is flowing through this confined region. So it has, in somehow we can say that this flow are similar, but physically the formulas that we obtain for solving flow through pipes would be completely different while solving flow through these rectangular shaped ducts. Okay, so in these kind of geometries we define a equivalent diameter or equivalent length scale to define the Reynolds number. So could anyone of you tell me what that diameter is called? Equivalent diameter is called?
Hydraulic diameter, sir.
Yes. So that is basically given by 4 into area of the confinement and the wetted perimeter. Basically the perimeter up to which the liquid has wetted the confinement. Okay. So for a fully filled confinement, the perimeter would be basically be the perimeter of the duct itself. So this basically the same. So if not explicitly mentioned in your problems that the flow is not completely filling the confinement, you can take the perimeter of the wetted perimeter. You can take the wetted perimeter to be equal to the perimeter of the duct. Okay. So I guess that's clear. So we have discovered coefficient of friction. This is also known as the Fanning's friction factor. Okay, this one. Okay, then now we basically look into head loss. So head loss, I guess the concept of head loss could be basically be said as a equivalent as an equivalent drop in a pressure head because of the case that the flow has to overcome because of the presence of viscous resistance in the pipe flow. Okay, and the expression for HF is given in terms of okay. So from our initial derivation, we found out that dP star by dz is equal to minus 8 mu v by r square. Okay. So yes. So represent dP star by dz as P out minus P in by L. So then this pressure difference, this pressure drop basically between P out and P in can be basically be written as rho g HF, where HF is the equivalent drop in the pressure head because of the fact that the flow has to overcome the viscous forces, right? So this P in minus P out we have substituted by rho g HF, where HF denotes the head loss because of viscous forces. Okay, so we equate this and then we get finally we represent R in terms of diameter. Then basically the numerator will be multiplied with a factor of 4, so it becomes 32 mu v. So and then we again represent this mean velocity in terms of the flow rate and the area of the pipe. So we can write that rho g hf is equal to 128 mu ql by pi dt by 4. And finally, if we substitute this in the denominator, we get hf is equal to 128 mu ql by rho g pi dt by 4. Okay. Again, this expression is known as the Hagen-Poiseuille equation, and this equation is special because the head loss is presented in terms of experimentally measurable quantities, because Q can also be measured, is basically can be measured in an experiment by, if you've done an experiment in your colleges, you know how to measure the mass flow rate. So basically, like if you open the valve, if the flow is flowing through a pipe and it is being stored in a container, if it's continuously flowing, then what we basically do is we open a valve where the flow is being stored and measure, say, like if you open the valve, then this flow that comes out of the valve gets stored in a this release of fluid from the valve can be measured through a scale that is being present, this already present in the device, and we basically then we can know the volume flow rate. And once we know this, so that volume of flow that has been passed, so we know that. So basically, if we know this volume, we can basically just measure time required for this volume of fluid to pass through that valve. So this will basically give us the volume flow rate. Okay, so that's why it is easily measurable in most other cases, like in your college experiments, as well as in industry. So Q is a very easily measurable quantity. Okay, that's why it is it is mentioned it is experimentally measurable. Then L is measurable because we know what would be the length of the pipe, because it is already it is quite easily measurable, and it's can be defined by the manufacturer themselves. Again, the same goes for D. Mu is again the property of the fluid itself. Rho is also the property of fluid. So these are also measurable. So that's why this formula is quite popular, or like quite useful, because these are all experimentally measurable and can give us a quite accurate or quite useful measure for HF. Now again, HF can also be represented in terms of fraction of kinetic energy head, basically because of the fact that some portion of the flow or some portion of the energy of the flow is being used to overcome this frictional losses, right? And that's why HF can be represented as a fraction of the kinetic energy head, the net kinetic energy head of the incoming flow. So what we do is we basically equate these two equations. Basically we equate equation 1 and 2, because 1 is now still in the form of average velocity. So that's why it is desirable that we use 1 instead of the final form. So we use equation 1 and 2. We equate those equations, and we finally find that F, that is the coefficient here, that F is equal to 64 by RED. Okay, and F here is known as a Darcy friction factor. Okay, and this equation is known as the Darcy-Weisbach equation. So again, we have a relation between F and CF. As you can see that F is 4 times the Fanning's friction factor, where CF was 16 by RED, right? That we initially found out by dividing the wall shear stress with half rho v square, right? So yes, then again I guess this is also mentioned that there is these two are bound to have a relationship, because this is found out by the equating the wall shear stress, and this is found out through the help of the pressure loss in the pressure head, and these two are equal. These two can be equated, and these two have a relationship because of the fact that it is because of the existence of the shear stress why we have and it is because of the existence of the shear stress because of which we have a pressure drop in our flow, right? So that's why these two are related, and this is the relation between the two friction factors. Okay, see, it is important to know that CF is derived through the fundamental equations that we derive from the velocity profile, and then we equate, then we found out the expression for tau wall, and then it is a, basically you can say that it is a analytically derived expression for finding the friction factor when uh, for finding the friction factor. But F is, you can say, is a is found out in a sense that the flow has to overcome a pressure drop, and like we here we don't extensively consider discuss about the wall shear stress, but it does exist because of the balance that we use here, because this equation is basically derived from that from the balance from the balance of the from the Navier-Stokes equation that inherently has shear stress. So we cannot directly say that this does not consider wall shear stress. It considers wall shear stress, but it is not explicitly mentioned here. So what we explicitly is present here in the equation is the pressure drop. So that's why, just to let you know the difference of how it was derived and how they are similar. So I guess it was clear. Again, to all this discussion, all this deriving the expression for the pressure drop or the loss in the or the shear stress that we discussed, finally boils down to the fact that these are some extremely undesirable properties that makes life difficult for all the industrialists, or say the people around, people or normal people. Why? Because say we want to pump the liquid from say from a lower level to a higher level. So right, in our homes also, I guess we have a storage tank at the bottom, and we want to pump this liquid to a higher storage tank through the help of a pump, right? Through the help of a pump, we pump this liquid. So the static pressure head that exists between these two storage tanks also need to be overcome by the pump, plus the viscous stresses that exist because of the flow of the fluid through the pipes is also need to be overcome, right? So this is undesirable. Like if these viscous stresses were minimal or didn't existed, then the power required to pump would only be the power required to overcome this static potential, static pressure head, right? So this is in that case undesirable, and thus the thus the significance of these viscous stresses comes in the application of in such kind of applications where this has to be pumped from lower head to a lower potential to a higher potential, and also when the liquid traverses long distances from the source to some other sinks. Say for example, like the fluids being pumped from the gas being pumped from the refineries to our from storage to our homes. So or fluids being transferred from the storage tanks to our home. In that traversing distance also it has to overcome the viscous stresses. So in those cases, the application of this pressure head loss because of viscous stresses comes into picture. And in this case, for pumping, the pumping power is basically being the expression for a pump power required to pump this liquid is being given by rho g hf Okay, so basically it is del p star q, where p star denotes the piezometric pressure difference. And if we need to consider this static pressure head, this will be given by power will be given by rho g q h plus hf. Okay, when h is this height difference, static height difference. Okay, so again I will briefly go through the, so I can say these are the basic concepts. These are all the basic, these are the entire basic concepts that are required to be known for understanding flow through pipes. So without these basic concepts, like understanding the concept of flow through pipes, uh, is quite difficult. So that's why I discussed extensively about the fundamental derivations of the Hagen-Poiseuille flow, and because it is what the precursor for learning the flow through pipes. Okay, so I guess this expression we discussed, Darcy-Weisbach equation, the head loss presented in terms of the fraction of the kinetic energy head. This we discussed. Again, this we also discussed. HF represented in terms of the experimentally measurable quantities. So this one is the Hagen-Poiseuille equation. Then we discussed about hydraulic diameter, that dH is equal to 4A by P, where P is a weighted parameter. And this right now we discussed the pumping power required to pump the liquid to overcome the viscous stresses, rho GQ H plus HF. So if H is not explicitly mentioned, then it will basically be equal to rho GQ HF. Like if it only asks in the question that the flow has to overcome, flow is flowing through a pipe with some friction factor, then if it's asked regarding the pumping power required, it is basically can be said that it is a horizontal pipe. So the power required will basically be rho G Q HF. Okay, if it is not explicitly mentioned, you do not need to worry about it. Again, so all these cases that we discussed for the friction factor was with the assumption that the flow is laminar, because it was the preliminary assumption that we took for deriving the Hagen-Poiseuille flow, right? So again, it is not necessary that for most of our day-to-day life cases, day-to-day life scenarios, that the flow would remain laminar. It can go turbulent, and it is actually turbulent for most of the cases. And to derive the expression for friction factor for these cases are found experimentally, and one of such expression is given by this: for hydrodynamically smooth pipe, F is equal to 0.316 Re, Re would be Red to the power 0.25. In the case where the Reynolds number varies from 4000 to 10 to the power 5. Okay, again, so just out of curiosity, okay, so up to what range of Reynolds number could you say the flow within a pipe remains laminar? What is that Reynolds number range? It can go plus minus 100, 200, that's fine, but do you know that critical Reynolds number?
4,000, sir.
4000.
Is it 4,000, sir?
No, it is not 4000. The critical Reynolds number for a pipe flow. Okay, it's fine, it's no problem, it's fine. For pipe flows, the critical Reynolds number is around the range of 2300. Okay, so it is not hard and fast. Okay, so if you find out Reynolds number to be say 2400, then also you can with a like very high precision you can use the assumption of laminar flows. Okay, it's not a hard and fast boundary that the moment it crosses 2300 the flow becomes turbulent, and if it is 2299 then a flow is laminar. It's not like that. Okay, it's just a demarcation or experimentally found demarcation that shows us that beyond 2300 the flow starts to show some turbulent behavior. Basically disturbances starts to grow, the disturbances that are being generated because of the roughness of the pipes starts to grow and can cause the flow to transition from laminar to turbulent. Okay, so that's why, and that's the whole concept of critical Reynolds number. So I also suggest you to learn about the concept of critical Reynolds number. And again, for flow over flat plate, can anyone tell what is the range of critical Reynolds number for flow over flat plate? What is the range?
Below 600, sir.
No, actually, and that's fine, no problem. Actually, for flow or flat plate, the critical Reynolds number lies in the range of 5 into 10 to the power 5. Okay, see, different geometries, different critical Reynolds number. Okay, this is what I wanted actually both of you know, that it does not mean that 2300 is a critical Reynolds number for all the geometries. Depending on the geometries, the critical Reynolds number could change. Okay, So that's why I wanted to introduce you to this concept. So I guess that's fine. Okay. Just out of curiosity again, since we are discussing about turbulent flows through pipes, so I believe Professor Chakraborty discussed about certain chart or diagram through which we could extensively or to a particular extent analyze turbulent flow through pipes. So could anyone of you please tell me what was that chart or diagram called?
Moody's chart, sir.
Yes, correct. It was the Moody's chart or the Moody's diagram. Okay. So I haven't discussed about it in today's session because I don't think like the exercise questions that we are going to discuss now are related to this. That's why, but it's my fault. I should have discussed. But since again it is a problem solving session rather than a repeat of the concept of lectures that we are go through, so that's why I didn't bother that much to discuss about Moody's diagram or extensively discuss about Moody's diagram. But still, I suggest both of you to look into the concepts of, or no, at least the steps how the Moody's diagram was used to analyze the turbulent flow through pipes. Okay, so that's a good practice. That at least, because if you find out that the Reynolds number that you're dealing with in the pipe flow is beyond say 4000, then you definitely know that the flow is turbulent. So your calculations of finding the friction factor F is equal to 64 by RED would not be valid, right? It's only for laminar flow, and that's why the concept of Moody's diagram comes into picture. That's why I encourage both of you to look into it. So again, I guess Professor Chakraborty briefly discussed about energy conservation in pipe flow. I won't go through it extensively. I encourage you to watch the lectures, because the only topics that I'm emphasizing more upon are the ones that we are going to use in our today's session, because for that you need your concepts to be very clear. So that's why I'm discussing those topics extensively. Okay, the ones that I'm not discussing does not mean that they are not important, but for those I encourage that you watch the lectures again. If you have any doubt, you can just ask in the forum or just mail me, since both of you have my mail ID, so you can just ask me there. Okay, so here alpha denotes the kinetic energy correction factor. Basically it was done to approximate the integration of the u cube term to in terms of the kinetic energy, that half m dot u square. In correcting, in approximating this in triple in it is u cube integral in terms of basically half m dot u square. In those in those approximations only the concept of the kinetic energy correction factor comes into picture. But so this was the expression for the kinetic energy correction factor. And for flow through circular pipe, we can write by substituting the expression for substituting the expression for the A and the elemental area, we get the expression for the kinetic energy correction factor for a circular pipe, and also defining the necessary limits. Okay, so again I guess then we briefly discuss about on the series and parallel connection of pipes. So okay, let me, before revealing it, let me briefly discuss about the electrical analogy. Like I guess both of you know about the Kirchhoff's current law and Kirchhoff's voltage law. Basically the series and parallel connection in electrical circuits, right?
Yes, sir.
Yes, right. So basically, like if we have a parallel connection, say it is R1, R2, R3. is I, this will again be I, so and this is V. So could any one of you please tell me, like, in this circuit, what is the potential difference between for the resistances R1, R2, R3? Are they the same or are they different?
Same, sir.
Same, right?
Same.
Why? Because they are in a parallel connection, right? And this is the very concept upon which the series and parallel connection are built upon. So for three resistors or resistors connected in parallel, the potential difference remains the same, but the current passing through each of the resistances could vary, right? Or it varies. That's why the current passing through all resistances are different, right? And it will basically be can be written as the equation of I equal to I1 plus I2 plus I3, and it is basically being can be written from the Kirchhoff's current law, right? Similarly, if these resistances are connected in series, say again, this is V, the net potential difference. This is V1. This is R1, R2, and R3, and this is the current that is I is the current that passes through the circuits. So in this case, what entity remains constant for all the three resistances?
Current.
Yes. So the current through all resistances remains the same, and the potential difference would vary, right?
Yes, sir.
Yes.
Yes, sir.
Yes. So basically, like, if V1, V2, and V3 was a potential difference, then V would be equal to V1 plus V2 plus V3. Okay. So exactly similar to this, if we try to find an analogy, and if we say we substitute current by volume flow rate, and voltage by head loss HF, the same analogy or the same concept could be used for pipes connected in series and parallel. So if I say two pipes, given this analogy, if I say that two pipes are connected in series as shown in this diagram, okay, having two different diameters d1, d2, can have different average velocities v1, v2, and different lengths L1, L2, and different friction factor. So given this scenario, if this pipe is connected in series, and you can say that this is the incoming Q, okay, and say this is HF1 and HF2. So what can you say about the volume flow rate between the two pipes? Would it be the same or different?
Same, sir.
Yes. So exactly similar to three resistances connected in series. For pipes connected in series, the volume flow rate through all these pipes remains the same. Similarly, now if we consider the head loss as potential difference, the net head loss between these two pipes would be the sum of head loss through the individual pipes, right?
Yes, sir.
Similar to what we discussed about the potential difference for resistances connected in series, right? So similar to that. So what we do is basically substitute the expression we obtain basically, like, if we write HF in terms of F L by D V average square by 2G. So we basically represent HF in terms of these entities. So we can write HF is equal to HF1 plus HF2. So I encourage that both of you very clearly look into these expressions, and at whatever point you may feel that you are unclear about the expression, you can just stop me and ask me to repeat it. Okay, so that's fine, I guess. So now if we represent HF in terms of these terms, we can write it as this. Basically we substitute V bar as Q by pi d square by 4. So since it is square, it becomes Q square, and 4 become goes to the numerator, so it becomes 16. So that's why the 16 term comes in the picture. So it becomes 16 FELE by 2g pi square d to the 5. So similar to the for the two pipes F1 L1 F2 L2 d1 to the 5 d to the 5. Since 16 2g pi square, this term is a constant, we can remove this from all the terms, and we can basically get FELE, where FE denotes the effective friction factor and LE denotes the effective length of the pipe. Say if we were to substitute this series of pipe into a single pipe, so the effective friction factor for that single pipe would be would be denoted by the FE, and the effective length for that pipe would be denoted by LE. So keeping that concept in mind, you can write FELE d to the power 5 is equal to F1 L1 d1 to the power 5 plus F2 L2 d to the power 5. Okay, and just and if instead of two pipes in series, if there are n number of pipes in series, we can just represent it in terms of summation. Say Fi Li di to the power 5. Say I varies from 1 to n. Okay, is this expression clear?
Yes, sir. That the effective friction factor and the effective length means also the friction factor for the equivalent pipe, sir.
Yes, like say if we were to say, instead of this pipe, if we were to consider a pipe with similar mass flow rate, the pipe that could give us the same functionalities of these pipes connected in series. So this pipe would have an effective friction factor of Fe and an effective length Le, and there's and relation of this effective friction factor and length of effective length would be given by this. Okay, this relation.
Okay, sir. Okay.
So Priyanka, is that clear?
Yes, sir.
Okay then, thank you. So similar to that, now we consider for, okay, I'm going to make the mistake. It should be pipes in parallel. Okay, so this was a mistake. So if I say these two pipes are connected in parallel, so the mass flow rate now no longer remains the same. So what remains the same is the head loss, right? Similar to the potential difference for resistances connected in parallel, the potential difference remains the same for all the resistors. Similar to that, for all the pipes connected in a parallel connection, the head loss remains the same, and the mass volume flow rate varies from pipe to pipe. Okay, so given that concept, we will have Q is equal to Q1 plus Q2, because the net volume flow rate must remain the same. Again, it is a outcome of mass conservation, so that's why. So Q must be equal to Q1 plus Q2, because there is no generation or storage of mass in removal of mass from this system. So the mass that goes through these two pipes must converge and give us the same mass flow rate. Okay, so it comes as a consequence of mass conservation. And as we said, the head loss remains the same for both of the pipes. We can just equate these head loss terms. Again, like if we were to substitute this this parallel connection with an equivalent pipe having the same functionality, say then if it has a friction factor of Fe and length Le, then we can say that, and say it will have a same head loss, say HFE, then we can basically write as HFE would be equal to HF1 equal to HF2, right? Because the head loss remains the same. That's why we write it and it is similar to the expression for HF that we wrote in our previous analysis for pipes in series. Similar expression 16 FeLeq square by 2g pi square d to the power 5. Okay, similar that we just equate it. See, these are equal signs, these are not added, so these are equal signs. So again, like if we consider the 16 by 2g pi square term as a constant, and we substitute that by c, say constant c, and then we, and again, like if we consider all these terms, say HFE equal to HF1 equal to HF2, say it is equal to another constant, say k. Okay, that I have written here. Then we can write these mass flow volume flow rates in terms of k and c, right? Say I'll write this one, okay, just to simplify for both of you. Say it is, then this will be, can be written as C F2 L2 Q2 square by D2 to the power 5. And since I said that all the head losses can be treated as a constant k, then k. Now if I wanted an expression for Q2, let's say Q2, then it will basically be square root of k d2 to the power 5 c f2 l2, right? So that is what I have basically written here. Q1 square is k d1 5 c f1 l1. Similar goes for Q2 square and Q e square. Now we again have a from mass conservation we get that Q is equal to Q1 plus Q2. So since these are Q square, you need to apply a square root to get Q2, Q1 and Q e respectively. So we basically get square root of d to the 5 divided by FELE is equal to square root of d1 to the power 5 f1 l1 plus square root of d2 to the power 5 f2 l2. So again, are these expressions clear, how it were derived and the concepts behind it? Is it clear, right?
Yes, sir.
Okay.
Yes, sir.
Okay, then we briefly discuss about similar dimension analysis. I won't extensively go and derive all the steps or discuss all the steps or extensively discuss as much that had been discussed by Professor Chakraborty, because in those two lectures, final lectures, I guess he have very beautifully and extensively discussed about dimension analysis, what geometric similarity, what kinematic similarity and what dynamic similarity means. So he has extensively discussed, so I do not find any point of repeating that again, but still, as a just to let you know about these concepts. So, dimension analysis basically comes into play when we are modeling fluid flows, right? So we might have seen flow simulations in wind tunnels or liquid tunnels, water tunnels, where you might have seen a geometrically scaled down version of planes, where you can see the in a wind tunnel they are being say if it was a wind tunnel, say if it is a wind tunnel, what we do is we use the geometrically scaled down version of a plane. Say this is our plane. Okay, I will zoom it a bit. Okay, so what we do is, now if you want to see the flow around this plane, what general practice is that we want to see the streak lines, right? As you can remember from the previous sessions, how basically it is the streak lines that we visualize rather than the streamlines, right? But in a steady flow case, if we assume the flow to be steady, the streak lines, the path lines and the streak lines, the path lines and the streamlines are similar, right? So what we do is basically we release some dye or smoke, say, and we then allow this smoke to this part of smoke to flow through above this plane, miniature plane. So it will flow to the plane, then basically over its wings, then over its tail, then below the wings, then again maybe generate a bit of wake, and then again converge, right? And again, like if you just zoomed further, you can see at the edge of the wings there will be some wingtip vortex generated because of the fact that the pressure at the upper end of the wing is lower compared to the lower end, and and that is basically the principle of generation lift. So like if this was the airfoil, the cross-sectional section of the wing, so the pressure at the lower region, or the pressure zone, and the upper part is known as the suction zone. So basically, if it is P1, sorry, if it is P1 and if it is P2, then P2 is greater than P1. So it will basically mean that there will be net force in the upward direction. So that will basically gives us lift, right? So I'm sorry that I'm discussing that much, but basically it is in this modeling, or it is in the applications of this modeling or studying or analyzing the flow through some geometries, there where the principle of dimension analysis come into picture, right? And say like in India, like it's very rare that we have a full scale wind tunnels. I guess there is one in IIT Kanpur, other maybe there, but I don't know extensive, but the IIT Kanpur one is quite popular. So I guess they have a full scale wind tunnel where you can model or study the flow through an actual scale or prototype of a aircraft rather than scaled down version. So but in most of the cases it's very expensive and quite difficult to run such simulations every time, and becomes quite costly, right? So what we generally do is we use a miniature scale model, such in this case, like that could be confined in a single laboratory, small medium sized laboratory, and then we simulate the flow over a aircraft. But again, it is very important that all these simulations must give us the same physical understanding that would have been obtained if an actual experimental analysis or flow analysis had been done over a real sized aircraft, right? The flow physics should remain the same. That's what I have mentioned here. The flow physics should remain the same. And as far as I can remember, Professor Chakraborty used a very beautiful example to show the difference, how the difference in scaling could change the flow physics, right? Could cause difference in the flow physics. Say like if you want to measure a flow, if you want to model a flow through pipe, right? Say our initial choice of diameter is say 5 meter, okay, 5 meter, and now we find that modeling flow through a pipe of 5 meter diameter is quite difficult for our within our budget. So what we do is now we use a 5 micron diameter pipe, okay. It is quite easily available and quite easily be done, since it is in micro scale, so it can be easily being confined to even a very small room, right? But again, as Professor Chakraborty said, even though it is geometrically similar, it is basically a geometrically scaled down version of the original prototype. This model is a geometrically scaled down version of the prototype, but still the flow physics do not remain the same. Flow physics become different. And why was the difference occurring? Like, I do not expect you to know right now correctly, but can you tell what flow physics might become significant in such a small scale?
Capillary action.
Yes, absolutely correct. So capillary action becomes quite significant in the case of such small scale pipes, which you might have studied in the earlier lectures when we discussed about capillary rise, how small diameter pipes, if inserted in a liquid, could cause a liquid head to rise above that small tube, right? Basically because of the capillary action, and that is occurring because of the surface tension effects, right? So those effects come into picture when we are dealing with micro scale. So, and this is not extensively visible or in the case of such large diameters. It's not that they are not available, but they do not come into picture, do not contribute much in the flow physics for such large diameter pipes, right? So these flow physics are completely different, even though they are geometrically similar. So that's why, if we are considering similarity, it is very essential that we consider all the three similarities, that is geometric similarity, that is similarity of geometry, kinematic similarity, that is similarity of the motion, and that will happen because of the similarity of the geometry. It is one of the precursors that the similarity of geometry is satisfied to have a kinematic similarity. And finally, the dynamic similarity, that is the similarity of forces. So that's why it is important. And right now, by now, I guess you know the difference between a prototype and a model. Uh, so can anyone of you please tell me the difference between a prototype and a model?
Sir, actual aeroplane is prototype. Scaled down version of it is a model.
Is it always scaled down, or it can also be a larger
It can be
version of
scaled
the?
up also.
Huh?
It can be scaled up also.
In which scenarios do you feel that it can be scaled up? Can you give me some examples?
Not sure, sir. Maybe some um, minute, some very small equipments that we use in medical industry.
Okay. Uh, I yes, maybe if you look into that fashion, maybe it may be correct. But I had more example that is quite relevant to fluid mechanics. Say like you know about some tiny bacteria or small organisms that traverse through a fluid domain using their say using their hair-like structures around their body, right? Say like if this was the bacteria, they have some hair-like structures. I am very poor at biology. I do not know what are they actually called, but and again in some cases they have a long hair that they use to propel past or propel within this fluid domain. Okay, and since it is maybe even very small scale, maybe in a micro scale, so this is basically a Stokesian domain because the scale is so small that the Stokesian nature of the Stokesian domain, basically the viscous nature of the flow becomes quite dominant. So these are Stokesian domain, and these are in the range of micrometer to nanometer, like if I'm not wrong. But still, I just wanted to say how they are quite small. And say now we wanted to simulate or understand the behavior of how these small organisms or bacteria propel past in a liquid domain using their these hair-like structures. So since they are so small themselves, there's no point of creating further scaled down version of these bacteria, which is practically impossible, right? So what we do is now we can try to make a scaled up version that is suitable for our experiments, and then maybe use a highly viscous fluid, even though it can be water in their case. But since the viscous effect becomes quite significant in the small scale, we can maybe use a highly viscous fluid and then try to analyze their behavior or motion in that experiment, right? That is suitable, that has a suitable scale for our that is that whose scale is suitable for our own benefit. So these are the examples where a scaled up version is also used. Okay, and also another example could be the flight of a fruit fly or a mosquito or a house fly, how they use their wings, how they use their wings to fly in the environment, how they use their wings to generate vortices that can propel them both forwards and backwards. So these are some of the examples. So I guess that's when I think I discussed quite extensively, but still these are important concepts that you need to know. Again, then the final topic for today's session in the course is the Buckingham Pi theorem. So okay, it is written on the screen, but still, could any one of you please tell me what's the Buckingham Pi theorem states? You know, right, the Buckingham Pi theorem. I guess Professor Chakraborty discussed about this in the final lecture, I guess. The Buckingham Pi theorem.
So, in several variables are combined into few non-dimensional numbers.
Yes, that is the final outcome of the theorem. But just the statement, just out of curiosity, like how clear you are regarding the statements. Could you tell me like what the statement was? I guess it is clearly written on the screen, but still.
n variables in a physical phenomena,
Okay.
and if these variables contain m fundamental dimensions like m, l, t,
Okay.
then the variables are arranged into n minus m dimensional terms, and each term is called pi term, sir.
Okay. Thank you. Thank you. I guess it's thank you for like being so generous for answering it. Actually, I'm just saying that because like it's very important. Like sometimes we mix up m and n and like may even like exchange the notations, right? So here m for my notation that I have used, so m basically denotes the all the physical parameters, and these parameters can differ from person to person. Like say Augustus is doing an experiment, okay? In his experiment he found out that there are 7 or 8 physical parameters that come into picture, that came in diameter, viscosity, density. I am saying fluid flow experiments, okay? Fluid mechanics experiment. Density, viscosity, diameter, then say flow rate, then maybe some other parameters, okay? Say some 7 or 8 parameters. And now similarly, like Priyanka has also done a same experiment, the same fluid mechanics experiment, but she found out that there are 16 parameters instead of 8. According to her analysis, she told that no, I think we need some more parameters for our analysis. So it does not always mean that a experimentalist who can find out more physical parameters would end up having a more accurate results. It does not mean that, but also it can also happen that the one who can find out more parameters to parameterize their experiments or analysis can end up having more accurate results. So that can also be the case. So the number of physical parameters that can be found out from in an experiment can vary from person to person depending on their perspective or how they view the experiment, how they view that the parameters can be essential. So according to Augustus, he may feel that the diameter of the pipe is an essential parameter that needs to be considered. But again, Priyanka may think that the diameter of the pipe is not that essential, but the length of the pipe that I think is more important rather than the diameter of the pipe. So it can differ from person to person. Okay, so that's why I'm saying that this can vary from person to person. Similar to that, like if physical parameters are changing, the number of fundamental parameters can also change, right? Usually it is the MLT that we usually discuss, the mass, the length and the time, but it may happen that Priyanka may be dealing with temperature also, so the Kelvin scale may also come into picture, right? So again, then Augustus can be dealing with number of moles, then the the number of moles can also be one of the fundamental parameters. So it can differ person to person, but it's very important to know that whether, since like most of the time when you are doing some experiments, these two are unknown, right? You need to find out yourself. So this is very important for anyone who is doing the experiment to decide it themselves and then do the experiment. Okay, so it may differ from person to person. That's why I was saying that. Okay, and so the Buckingham pi theorem basically states that if m is the number of physical parameters in the experiment, n is the number of fundamental parameters, basically the fundamental scales that are available in the experiment, then the number of non-dimensional parameters by which we can completely or define our experiment or our analysis is given by m minus n. Okay, so this is basically the Buckingham pi theorem, and all these parameters are non-dimensional, and thus these non-dimensional terms are giving the name pi. Okay, these are given the name pi terms. Okay, so if you again read extensively, you will know the importance of non-dimensionalizing the parameters rather than having dimensional parameters, how having non-dimensional parameters can reduce the number of parameters that are existing in a problem, and it can be helpful both for the reader and the experimentalist. So that's what you get to know when you study like again and again. So that's fine. So this is it, I guess, regarding the concepts that we need to know. So you might be thinking that almost finished the session discussing only discussing the theory and not solving any problems. So basically the thing is that the problems that we are going to discuss are very simple and are mostly based on the concept that we have extensively discussed in today's session. So okay, then for the remaining time, let us go through some of the problems. These are quite simple. I do not think that it will take much more time, but still, let's see. Okay. Consider a pipe. Let's go to the first question. Okay. Consider a pipe that branches out into two parallel pipes and then rejoins at a junction downstream. The two parallel pipes have the same length and friction factor. The diameters of the pipes are 3 cm and 6 cm. If the head loss in the 3 cm diameter pipe is 0.64 meter, the head loss in the other pipe is given by
Option D, sir, same 0.64 meter.
yes. And Priyanka, what do you think?
Same, sir.
Yes. So I guess these are one of the tricky questions that come into the exams or competitive exams, that they give you such a long question, but at the end these are two parallel pipes. So and even the head loss is given. So the basic fundamental concept of parallel pipes is that HF1 should be equal to HF2, and that's why it will be equal to 0.61. Okay. Again, just one more like side note or some important or useful thing for both of you to know is that these topics, that flow through pipes and dimension analysis, are like one of the such topics from which these competitive exams give like most of the questions. Like there are many times you can see that from the fluid mechanics subject, there are many questions that come from these concepts. Why? Because they are mainly formula based and conceptual. Like basically they are conceptual, right? They are, if you know the concept, you know the answer. So that's why these topics are like very popular among the competitive exams. So like if you both of you are planning to give GATE or ESC, in that sense, if you know the formulas, then like these topics could be very easy for you. Like it's just the substitution of the values in the formulas and you get the result. Okay, just as a side note. Okay, question number 2. The two pipes of the identical length and material are connected in parallel. Okay, identical length and material. Diameter of pipe 1 is 4 times the diameter of pipe 2. Okay, D1 is 4D2. Assuming friction factor and pipe length to be the same in both cases, and disregarding minor losses, the ratio of flow rates in the two pipes are given by, so you need to find Q1 by Q2. So I would say it's very simple again. Just look back into the formulas that we discussed. It is right in front of you, the formulas. You need to just substitute the values and find the ratio of Q1 by Q2. It's very simple.
Sir, 32, sir.
Okay, so Augustus has his answer is 32. So Priyanka, what do you think?
So 32, sir.
Okay. Okay, then it's since both of you are giving the same answer, it is correct. 32 is the correct option, and I guess both of you basically equated the head loss for both the pipes, right?
Yes, sir.
Yes. So I don't think
Yes, sir.
I need to show the steps. It's very simple. Okay. So question number 3, again is very simple. Pipe A is connected in series with another pipe B, whose diameter is twice and the length is 8 times that of pipe A. So it is basically given. If both pipes have the same friction factor, the ratio of frictional head loss of pipe A to those for pipe B is given by, basically you need to find HFA by HFB. Again, this is also very simple.
So 4.
4. Okay. Augustus, did you get an answer? I guess
Yes, sir. 4, sir. 4, sir.
okay. Again, since both of you are giving the right answer, I don't think I need to show the steps. So I guess you basically equated Q1 equal to Q2, right?
Yes, sir.
Okay. I guess it was quite simple. So let's then jump to the final question. Final question, because it is a common data type question. So okay, let me read it. A rotodynamic fluid machine of a given shape and handling an incompressible fluid. The relevant variables involved are d, the rotor diameter, q, the volume flow rate to the machine, n, the rotational speed of the rotor, gh, the difference of head across the machine, that is energy per unit mass, rho, the density of fluid, mu, the dynamic viscosity of the fluid, and p, the power transferred between the fluid and the rotor. I guess it is similar to the example that we are discussing, the pumping of pipe from lower head to the higher head. So we are discussing about pump. With the help of Buckingham pi theorem, the relationship between the variables can be expressed by a functional form of the pertinent dimensionless parameters as f, pi 1, pi 2, pi 3, pi 4. Okay, so I guess I simplify the problem by saying that there are 3 fundamental parameters. So that simplifies the problem itself. So okay, the first question itself was like that, so I don't think you need to solve it. The number of fundamental dimensions in which the variable can be expressed is equal to, I guess it's 3, so I do not think you need to solve it. It's quite simple, it's quite obvious from this expression, because there are 7 parameters and 4 pi terms, so basically 7 minus 3 fundamental parameters, so that's fine. Okay, so let's see question number 5. Okay, if pi 1 equal to q, I can zoom it, I guess. If pi 1 equal to q rho a1 n b1 d c1, then the values a1, b1 and c1 are, just asking out of curiosity, you know, right, how you find the pi terms from the Buckingham pi theorem by matching the dimensions of both the LHS and RHS. Basically the dimensions and the LHS would be 1, it will be unitless, so it will be 1, and you need to equate the exponentials to 0, right? You know that there's steps, right? Or should I show you one should I show you one example so that you can do the rest of them?
Yes, sir. One example, sir.
Okay then, I guess I did it in, okay, this is it, I guess. Okay, so in that case, I guess the crucial step in the Buckingham pi theorem is basically the initial step, that is choosing the repeating variables. Okay, and I guess Professor Chakraborty discussed about the properties that the repeating variables should follow. First is that all the repeating variables should contain all the fundamental dimensions. Okay, for this first step. Secondly, they themselves should not form a non-dimensional number. Basically, like dn by rho should not be non-dimensional, or d rho by n should not be non-dimensional, or d rho n should not be non-dimensional. Okay, these were some of the prerequisites of choosing a repeating variable. And and for our case, or I must say, the most popular choices of repeating variables are basically one length scale, one velocity scale, and one flow property. Okay, one flow property. So if you choose rho, then you should not choose mu as one of the repeating variables. Okay, either one of them, either rho or mu. Okay, and here P is not a pressure, P is the power. That's why I'm not choosing pressure, and that's why I'm not choosing P. Okay, so D has a length scale of length. It is quite simple also, so I am choosing D as one of the repeating variables. Again, N has a length scale of velocity, but actually it is the angular velocity. They are giving rotational speed, right? So its length scale would be t to the power minus 1 rather than lt to the power minus 1, because velocity has a scale of lt to the power minus 1, but since it is angular velocity, so it will have a scale of t to the power minus 1. Okay, and I choose the next repeating variable as rho. Okay, density instead of mu. I could have chosen mu also, that's not a big issue, but I choose rho. Okay, so these are some of the precursors, but it's not like that if you choose other ones you will not get the answer. But the thing is, it would become quite tedious and quite difficult, because you have to again check again and again whether all the dimensions are considered or not, whether they form a other non-dimensional number or not. So it's best to choose some simple repeating variables, having simple dimensions. Okay, so I choose my repeating variables as d, n and rho. Okay, I should write it, I guess. D has a dimension of L, n has a dimension of t to the power minus 1, and rho would have a dimension of mass per unit volume, so ml to the power minus 3. Okay, so say pi 1 in the question itself, they are given that pi 1 is need to be evaluated by q rho a1 n b1 bc1. Okay, and funnily enough, I didn't look through it, but they have given the choice of our repeating variables themselves, right? So it simplifies the problem even further. So I am thankful that my choice and their choice are similar, but still. So I read pi 1 is equal to q rho 1 and nb and dc. Okay, so the dimension of q would be meter cube per second, right? Meter cube has dimension of L cube, so I write L cube t to the power minus 1. Then rho I know dimension, so ml to the power minus 3 to the power a. N has dimension of t to the power minus 1, so t to the power minus 1 b. And d has the dimension of length, so L to the power c. So is this step clear? Up to this step, is it clear? Is it clear up to this step? Priyanka and Augustus?
Clear for me, sir.
Okay, okay. Okay then, I guess that's fine then. So what we do is, now we club in all the exponentials for all the for each fundamental variables. Okay, so for L we see that there is one 3, then there is minus 3a, and there is one c, right? So L would have a power of L to the power 3 minus 3a plus c. T has a one minus 1 and one minus b, so minus 1 minus b, and m has only one power, it is m to the power a. Okay, so in the right hand side, as I told, the pi terms are dimensionless, so this would basically have an exponential power of 0, right? Say if you basically be some based on some fundamental dimensions to the power 0, right? So since m has a power of 0, so basically a would be equal to 0. Okay, equating the LHS and RHS. I should write it again. So equating the powers of in the both sides, so m has a power of 0, so a would be equal to 0. Then we look into t, so minus 1 minus b should be equal to 0, so it basically gives us b equal to minus 1, right? Again, for L, 3 minus 3a plus c would be equal to 0. So we have that a equal to 0, so 3 plus c is equal to 0, so it basically gives us c equal to minus 3, which is what we get. Okay, actually in the question they have only asked us the value of a, b and c, so we got a as 0, b as minus 1 and c as minus 3. So let me cross check. Yes, so the correct option would be c. Okay, is it clear?
Yes, sir.
Okay, then I guess I did question number 5 for you. Then you can similarly do for question number 6. For pi 2, basically you replace q by gh and then repeat the similar steps and give me the value of a, b and c. Okay, I guess question number 6 would do good for today's session. I don't think it's worthy to repeat the similar steps for all the terms because it's just mathematical calculations. I don't bother that much regarding that, but at least do one for me, and this will be that for today. Okay, just do pi 2 for me, that's all.
Sir, option B, sir.
B.
Second one, yes.
Okay. So Priyanka has found the answer to be question option B. Augustus, you can also tell once you are finished. So just tell me the answer. Okay. It's quite simple actually. Just mathematical manipulations and calculations. Simple algebraic equations, not at all difficult. But as I told you, the most crucial part is the initial part, that is choosing the repeating variables. And here they've already given us, but we might have done by using mu instead of rho. That could also have been one of the options. So that's it. But like, it comes in through practice. Like once you read the textbooks, you see solve examples, you will eventually get to know like what are the best choices of repeating variables given the physical parameters that are available in the problem. So it comes through practice and understanding of this concept. So I guess it's not a big deal, but it's just that it comes through practice. So that's fine. Augustus, so did you make any progress?
So I'm still working out. It seems it may take some time, but I know the concept. I will try, sir. No problem.
Okay, that's fine. I guess it's very simple, right? Since we are time bound, that's why I was emphasizing. But solving any problem in a given amount of time is not a like the most important thing for any student or anyone who is going to learn, right? It's basically the concept that we catch while learning these things. So that's more important. So I guess that's fine. And actually, option B is the correct option. So let me just go to my calculations. Okay, so I took some time just to represent those pi terms in terms of non-dimensional values. So for question number 5, since we find out that a and A, B, and we found out a value for A, B, and C. I found out that pi 1 is given by Q n d cube. Okay. Similar to that, pi 2 was given by GH n square d square. Then we find out pi 3 is mu rho n d square. So I guess it is a very it's quite well known. It has a similar structure to one of well known dimensionless number. Could any one of you please say pi 3 is similar to one of the popular dimensionless numbers? Similar structure, may not be exactly the same, but similar structure. Yes.
Sir, Reynolds number similar, not exact.
Yes. It is actually similar to Reynolds number. Like basically, like if you write it as mu rho d and nd, so this will basically give us the velocity. So I'm just trying to find out some relationship. That's what I told, like similar to Reynolds number but not exactly to Reynolds number. And finally the final non-dimensionless number is given by p rho n cube and d to the power 5. So the basic motto behind me showing you these non-dimensional numbers are actually is because like once you study about turbo machineries, because this question was based on the concept of turbo machineries, basically pump that he discussed, rotodynamic pump. So once you deal with the when you study about turbo machineries, basically some centrifugal pumps, say, you will come into contact with some of these numbers again. So those will be given some name as specific head, specific power, specific velocity, specific speed. So these terms you will get to know once you read about turbomachineries. And here, if you recall the structure of these non-dimensional numbers, these are exactly the same numbers that you will eventually encounter while you are studying turbomachineries. So this was the main motive behind me showing you the actual structure of these pi terms. But still, I hope that more importantly you got to know how to implement this Buckingham pi theorem. That was more important agenda for us to complete. But still, so I feel this is all for today's session as well as for the entire course. So
Sir, one small doubt may I ask,
sure,
sir?
sure.
Regarding week 12 assignment, there was a question involving Weber number.
Okay.
So, could you please guide us on the concept to solve that question, sir?
Actually, the thing is, I also don't know the question that we are dealing with. So I have your mail. I will give you some help regarding the question. Is that fine?
Okay, sir. Okay, sir. That's
But
fine.
I also didn't see the question because these are the questions that we are asked to solve and teach the students. So that's what I did. But I will look into it. Okay. I guess it will be similar, but still, let me try and help you out. Okay.
Okay, sir.
Also, I insist you to just put this doubt in the discussion forum. Some other tutors may also find it interesting and answer your question. Okay. Okay then. So this is all from my side, I guess, for this course. And again, I would like to thank both of you for being so punctual and so attentive in the classes. Like both of you have done excellent in solving the problems, understanding concepts, and like helped me as a tutor to carry on the classes and motivated me to do more and more to help both of you, or like all the students that were there, but especially both of you, since both of you were here regularly. So motivated me to be a better tutor and teach you the concepts in a better way. So there might have been some cases where I may have made some mistakes or couldn't teach the concept properly, so I apologize for that. But still, you have the video lectures. They are the greatest source of knowledge, and I ask you to go to lectures of Professor Chakraborty. Basically, I was talking about his lectures. And also, if you have some doubts regarding problems, you can look into these my video lectures, my problem solving sessions. It may also be turn out to be helpful. But still, from my side, I will insist both of you to read and try to understand the concept and solve as much problems as you can, so that you get clearer and clearer. Okay, and have a strong grasp on the subject. So that's all from my side. So any feedback from both of you regarding these problem solving sessions? Like in the 6-week session, I guess I asked about the feedback, but again, since today this is the last session and the last class, I guess I also would want some feedback from both of you. So you can tell one by one. That's fine. Yes, please go ahead.
Hello, sir.
Yes, please go ahead.
Sir, thank you so much, sir, for conducting these sessions. They were very helpful. And coming to the problems, like usually in like class courses, we just solve the problem, get the answer, and we are done with it. But through your live sessions, like we're not just solving the problems, we are also delving to the concepts behind it. So it was a different perspective for me.
Oh.
And
Yes, please go ahead.
and the live sessions by Professor Chakraborty, sir, they were very good, sir. But like between like those sessions, those sessions were recording, so like there was a gap between those sessions and me listening to them. I think the gap was filled by you, sir.
Okay.
Like if any doubts, any concepts,
Okay.
it enhanced it more, sir. So thank you so much.
Okay. No. Thank you to both of you. Like it is also a first time experience for me also as a tutor. So I also get to learn more. And it's told that like the more you teach, the more you learn better. Like you learn better yourself. So it was also teaching, learning for me also. So thank you, Priyanka. Thank you for your beautiful feedback. I hope that you work hard and become an expert in the field yourself one day, so that others can learn from you also, including me. So thank you. And Augustus, what is your feedback? Could you please share your feedback? So yes.
Sir, thank you for your valuable guidance, and your explanations were very much helpful in knowing how the various difficult problems of each sessions can be solved.
Okay.
So it will be surely helpful for us in the exams, sir.
Okay. Okay.
Without these problem solving sessions, we would have faced so much difficulties in understanding how to solve these problems.
Okay. 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 Thank you, Augustus. Thank you so much. I'm really happy that I was help both of you even a bit from my side, since both of you or all other students that attended the sessions solved the problem themselves, and I was just trying to tell them where they made the mistakes and by showing them my solutions so that they could learn. But still, both of you and all the other students like gave extensive efforts to solve the problem themselves, understand the concepts by working hard themselves. And obviously, at the end, but not the least, the guidance that we all followed, that is Professor Chakraborty. His lectures were the source of knowledge for each and every one of us. So we thank him also. So thank you both of you. I hope that we might meet again in some different subject or different problem solving sessions. But I wish both of you best of luck for your future endeavors. Hope to meet you again, maybe, but still, best of luck to both of you, and good luck for the exams and for your life ahead. So, okay, thank you. Yes,
Thank you very much, sir.
thank you. Okay then.
Sir,
Oh yes. Okay, yes, please.
may I just ask a question, like not regarding the subject?
Sure, no problem. Yes.
Like personal question, sir. You did your post graduation in like thermal domain, sir?
Okay. Yes. So, what I can do is I can stop the recording right now. Then we can stay in the call and then discuss. Is that fine?
Yes.
Okay. Okay then.